Today we're going to talk about ANOVA tests. ANOVA is an acronym, stands for Analysis of Variance, and it's a statistical method that's used to look for differences in means among more than two groups. We saw last time how we could compare two different groups and look for differences in means or proportions, depending on whether we had a quantitative or a categorical variable. But with ANOVAs, we're going to be dealing with a quantitative variable, so we're definitely looking for mean differences. And we have multiple different groups. The example that I have up on the screen here deals with 4 different brands of golf balls. Brand A, B, C, and D. And in this particular experiment, what was done is they took a mechanical driver called Iron Byron and hit 10 different golf balls of each brand, and they measured the distance that flew. And we were trying to find out then statistically if there's a difference in how far those different brands of golf balls fly. If you're a golfer, at least as long as you're hitting it straight and in the fairway, you'd like to know that it goes as long as possible. So we can't use the Z stats or the T stats or the proportion stats like we used last time because we have more than 2 groups. So this calls for an ANOVA test. We'll go to our stat button, and we do have an option for ANOVAs here. And this one is actually a one-way ANOVA. It's one way because we only have one factor, one variable that's creating our different groups, and that is the brand of golf ball. So one-way ANOVA, we're going to use our columns here for brands A, B, C, and D. And I'm holding down the control key as I select each of them so that I get all of those. And the other thing that I want to check, and I'll explain why here in a minute, is I want to check this option down here to compute the 2 keys test. More about that in a moment. One other thing that we could do is we want to do the Levine's test for the homogeneity of variance. Again, more about that in a minute. We go ahead and click Compute. And let's see what our results tell us. First of all, it gives us just some statistics for each brand. We can see that there were 10 observations for each group. It gives us the mean, standard deviation, etc. for each of those. We can see that brand C did fly farther than the other 3 brands. But the question is, was that a significant difference? Can we reject the null? Can we conclude that for all brand C golf balls, would they fly farther in that situation? And this next table gives us that answer. We look at the p-value, less than 0.0001. We do have a significant result. We can reject the null and conclude that there is a significant difference among how far these different brands fly. What we don't know yet is exactly where that significant difference is. This next table gives us the Levine's test for variance, and this gives us a p-value of 0.9973. Now you may be thinking, oh, well that's not significant. In this particular case, that's a good thing. We want the p-value for the Levine's test to be greater than 0.05 because the ANOVA test, the way it's set up, it's kind of sensitive if that Levine's test comes out to be significant. If it has a less than 0.05 p-value, kind of have to throw out all of our other results. So we want that particular p-value for the Levine's test to be greater than 0.05, and it is, so we're good. That brings us down to these 2 keys tests, and this is where we can determine where the actual differences are. And it does what are referred to as pairwise comparisons. It compares each set of 2 brands to see if there are significant differences here. So here for brand A, subtracted from brand B, gives us a difference of 10 yards per ball. That's a significant difference. So brand B flies significantly farther in this circumstance anyway compared to brand A. Any of these pairwise tests that have p-values less than 0.05, so basically that's going to be every single one except for this one, the comparison between brand A and brand D. The p-values less than 0.05 tell us there's a significant difference between those two brands. What we're going to look at next, though, is what happens if we interject some other variables into the mix. In this particular situation, we had iron Byron there, so there wasn't really a lot of difference. We had a machine hitting the golf balls. But if you're going to go out and play golf, you probably don't have a machine to hit the golf balls for you. So what if we had actual people hit the golf balls? Maybe that would make a difference. And so what the next experiment that was designed was they took 10 different golfers and gave each golfer one of each brand and had them hit those golf balls. So we still ended up with 10 of each brand being hit, but they were hit by 10 different people, one for each brand, instead of all being hit by a machine. And so we want to see if we get the same results with people hitting the golf balls as opposed to our driving machine. This is what's called a randomized block design or a repeated measures test. We're taking A, B, C, and D and then repeating that test with each of 10 different golfers. And actually having it set up in this second method where we have the golfer, the brand, and the distance listed is going to be more beneficial to us here. We'll go to Stats and ANOVA. This is our repeated measures test. So we go there. The responses or the outcome variables are in the distance column. The treatments, what we actually are interested in seeing if there's a difference in, is the brand column. And our blocks, the chunks of data for each of our different individuals, is in the golfer 1 column. We click compute. And once again, we can see that our p-value is less than 0.05, so there is a significant difference in the distance that those golf balls traveled, depending on the brand. And once again, if we look at the mean here, we see that brand C has flown farther. Well, now, if you're the manufacturer of brand C, you're feeling pretty good about yourself right now. You're thinking, hey, we have statistically significant evidence that our golf ball flies farther when it's hit by a driver in a mechanical machine and by humans. But some of these other golf ball brand manufacturers said, well, wait a minute. You don't only hit a golf ball with a driver. What if we use other clubs? Maybe some other ball would fly farther if it's being hit with a different club other than just the driver. Now we're introducing 2 completely different factors or 2 independent variables that we're interested in measuring the effect. We want to know the effect of the different brand of golf ball, and we want to know the effect of the different club that's being used. And in fact, we're also interested in whether or not there's an interaction between the 2. Whether maybe one golf ball brand flies farther with the driver, but a different one flies farther with a different club. So that's what we're going to look at now with a factorial design. I'm going to open up GLFAC1 as my data file. And unfortunately, the way they set these up is not in the right format that we need to have to do our test. So we have to do a little bit of modification here. I'm going to set up all of my distances in column A. I can leave the A's alone, but I'm going to need to copy the distances from columns B, C, and D. So I'm going to highlight those distances in column B. I'm going to hold down Control and C. Click over here in column A and do Control V to paste it in. Go to column C, Control C, come back here, Control V to paste it in. Control C, Control V. Now I've got all of my distances in one column. I'm also going to have to get my clubs and my brands in one column. With the club, it's going to be kind of easy. I can Control C to copy it one time, and then Control V to paste it 3 different times. That put the clubs all in one column. For the brand, it's going to be a little more difficult. I'm going to create a new column over here called brand, and I'm just going to have to type it in. A for the first 8 observations, B for the next 8 observations, C for the next 8 observations, and D for the final 8 observations. It's definitely not ideal that we have to make those kind of modifications, but we do need everything set up in separate columns here. Now we can go to our ANOVA test. This is a 2-way ANOVA because we now have 2 different factors that we're interested in, the brand of golf ball and the club. Our responses are in column A. That was the distances that they flew. The row factor is the club. Column factor is the brand. We want to display the means table, and we can compute our Tukey's post-tests here. Now within our ANOVA table, it doesn't just give us one p-value for our result. It gives us 3 different p-values. The first one is based on the club. And that p-value is less than 0.05, so that tells us that there's a significant difference in how far those golf balls fly, depending on which club you use. Well, that should be a no-brainer. We used a driver and a 5-iron. The driver should hit the ball on average farther than the 5-iron. But now we've statistically proven it. We also get a p-value less than 0.05 for the brand. So it made a difference which brand of golf ball we used. But further, there's a significant difference here, p-value of less than 0.05, for our interaction effect. Or in other words, there was an interplay between the club and the brand of golf ball. And looking at our means table here, we can see what that interaction was. With the driver, brand C went the furthest. Well, that matches up with our previous tests. That's not a surprise. But look what happened when we switched to the 5-iron. Now brand B has the highest mean. Brand A actually is still higher than brand C. So brand C dropped from first all the way down to third. So it's not all lost for some of our other golf ball manufacturers, because they can still argue that, well, the brand C might fly farther with the driver, but you're not always going to use your driver. What if you're using something else? You may need to use the different brand of golf ball. Down below we have the Tukey's test, so we could go through and compare each pair of differences. And again, just like we saw before, anywhere that the p-value is less than 0.05, that tells us that there's a significant difference here. So for example, in our table comparing the 5-iron with hit with brand A, there was a significant difference between the driver hit with all of the different clubs, not a significant difference between the 5-iron hit with any of the other brands. So you can just go through and look at those p-values for the Tukey's tests. Wherever it's less than 0.05, you have a significant difference there. And that is how you do ANOVAs. When you have more than two groups and a quantitative variable.